and talk about aldehydes and ketones, Chapter 19, which deals exclusively with aldehyde and ketone chemistry. Keep in mind that this is a 3-lecture chapter, so it is one of the longer chapters in the 3rd edition of Klein. So let's get started right away. And first we'll identify the functional group in an aldehyde and a ketone, or clarify what that is. And by now I'm sure you all know what an aldehyde and a ketone are, but let's just go over it again. An aldehyde is when we have a carbonyl group. So remember, a carbonyl is a carbon that's doubly bonded to oxygen. So an aldehyde and a ketone, they both contain a carbonyl group. But the aldehyde has an R group and a hydrogen on either side, and the ketone has 2 R groups on either side. We also find carbonyl groups in esters, carbamates, amides. So a carbonyl, a carboxylic acid. But again, here's the structure of an aldehyde and a ketone. And of course, aldehydes and ketones come up all over the place in both biology and in the pharmaceutical industry, synthesis, oil and gas industries. The simplest aldehydes and ketones are shown down here. Formaldehyde, you're probably aware that formaldehyde is used as a preservative, and acetone is in fact mostly used as a solvent. In fact, it's found in nail polish remover. Acetone is also really good for washing glassware. I know we don't do that in the lab at UCCS, but oftentimes when you have compounds that are insoluble and maybe stuck to your glassware, acetone works really well for washing glassware. You can also purchase it at Home Depot or Lowe's or something in containers in the paint section, and you can use it as maybe a paint remover. Anyhow, so aldehydes and ketones. These are some examples of aldehydes and ketones that are found in nature. Vanillin, which is vanilla flavoring. You can see that not only does it have an ether and a phenol, it's also got an aldehyde in it right here. Cinnamaldehyde, which is cinnamon flavor, has an aldehyde, as does carvone, has a ketone in it. Carvone is, if you smell carvone, it has that strong spearmint flavor. And then, of course, benzaldehyde, which is almond flavor. Also, progesterone and testosterone, which are the female and male sex hormones, both have ketones in them, and that's also denoted in their names, which end in "-one", which denotes that it's a ketone. And with that in mind, let's get into the nomenclature. And how do we go about naming aldehydes and ketones? And it says here that we have 4 discrete steps to naming an aldehyde or a ketone. The same procedures that we used for naming alkanes and alcohols. So first we're going to identify and name the parent chain. Then we're going to identify and name the substituents, chloro, bromo, methyl, ethyl, sec-butyl, whatever. Then we're going to assign a locant or a number to each of the substituents, 2 ethyl, 3 methyl, so on and so forth. And then we're going to assemble the name alphabetically. So if you've been keeping up with your nomenclature thus far in the course, you can extend a lot of those things that you've learned into naming aldehydes and ketones. Again, number 1 is to identify the parent chain. For aldehydes, you replace the E from the end of the alkane with al, so butane becomes butanal. Methane would be methanal, ethane would be ethanal, propane would be propanal. I could keep going, but you probably don't want to hear any more. The parent chain always has to include the carbonyl carbon. Here's a really good example. At the bottom, if we look at this alkane, you can see that the longest carbon chain contains 8 carbons, and that's the chain that's highlighted in red right here. 1, 2, 3, 4, 5, 6, 7, 8 carbons like this. Now, if we were to have a carbonyl for an aldehyde at this carbon right here, then when we're naming the compound, remember that parent chain has to include the carbonyl carbon, and thus the longest chain would only have 1, 2, 3, 4, 5, 6 carbons. The aldehydic carbon is always assigned number 1. Now this is an example of a trifunctional compound. We don't look at a lot of bi and trifunctional compounds in our class, but if we take a look at the functional groups in here, we have what? We've got an aldehyde, so we have an aldehyde here, we've got an alcohol here, and we have an alkene right here. So 3 functional groups. Now, our book doesn't cover what's called the order of precedence of functional groups, but what I can tell you is that the higher the oxidation number of the carbon in the functional group, it's going to take the highest priority. So an aldehyde is at a higher oxidation state than an alcohol or an alkene, and so it's going to take precedence. So what I'm trying to get at is if you were to look at this compound and talk about it with a friend, you'd say, well, is it an alkene, is it an alcohol, or is it an aldehyde? You would describe it as an aldehyde. Anyhow, again, our book covers very, very few examples of this. So we would, of course, assign that carbonyl, carbon of the aldehyde, carbon number 1, and then we would number going off of that. For ketones, the suffix "e" in an alkane is replaced with "one." So butane becomes butanone, pentane would be pentanone, hexanone, heptanone, octanone, nonanone, decanone, undecanone, dodecanone, so on and so forth. The parent chain has to include the carbonyl group. Now, unlike aldehydes, where the carbonyl carbon was given the number 1 always, because an aldehyde is always going to be at the end of a molecule, the carbonyl carbon in a ketone is simply given the lowest possible number, and it can be expressed either before the parent name or before the suffix. And we saw that with alcohols as well. Let me give you an example that's shown down here at the bottom. We have a ketone. Clearly, there's a ketone here. The longest carbon chain contains 7 carbons. We give the carbonyl carbon the lowest possible number, which would be a 3 instead of a 4. And we could call the compound 3-heptanone or heptan-3-one. Either one is perfectly acceptable according to IUPAC rules. If we have a stereocenter in an aldehyde or a ketone, of course, we have to designate the configuration of that chiral center, and we always place that at the beginning of the name. Here we have R2-chloro-3-phenylpropanol, so you always want to be up to speed on your Kahn-Ingold Prelog rules. Here's our chiral carbon. We have a hydrogen coming out in front like this. The chlorine takes the highest priority. This group takes second highest priority. This group takes third, and obviously the hydrogen takes fourth. If we follow these groups going from 1 to 2 to 3, you can see that we're going counterclockwise, which would be S. But since our hydrogen is coming out in front, we reverse that, and we end up with the R designation for our stereocenter. If you have an aldehyde attached directly to a ring, we call that a carbaldehyde. So if you have this compound, this would be cyclohexane carbaldehyde. I mean, you can come up with all kinds of different examples, but if you had a 4-membered ring in an aldehyde like this would be cyclobutane carbaldehyde, so on and so forth. So a carbaldehyde. It says here that IUPAC also recognizes the following common names as parent names. There are many common names that are used for aldehydes, and we only look at a few. Formaldehyde would be the common name of a 1-carbon aldehyde. The IUPAC name of this would be methanal, right? Because there's only 1 carbon in the molecule. If I have 2 carbons in an aldehyde, this IUPAC name would be ethanal, or the systematic name, whatever you want to call it. The common name is acetaldehyde. And then finally, benzaldehyde is the common name that we use for this compound shown at the end. All right, let's take a look at some nomenclature practice in a second, but before we do that, I want to go over these other common names for small aldehydes. Now, the only 2 that I had previously in previous versions of this slideshow were these first 2 here, methanal and ethanal, which are formaldehyde and acetaldehyde. But just to put the bug in your ear, if you have propanal, its common name is propionaldehyde. If you have butanal, its common name is butyraldehyde. And if you have pentanal, its common name is valoraldehyde. You might see those around if you're the kind of person that likes to peruse the internet to look up more information about what we learn in the chapters in this class. All right, here's where I was getting to. I wanted to try some nomenclature practice. The first compound is an aldehyde in 19.1a. Of course, we want to identify the longest carbon chain, which I think is pretty abundantly clear in this compound. This is the longest carbon chain. It has a total of 6 carbons, And we want to number that carbon chain in such a way that we give the carbonyl the lowest possible number. Now, when it's an aldehyde, the carbonyl carbon is going to be given the number 1. So we have 1, 2, 3, 4, 5, 6. So this must be some kind of hexanyl because it's an aldehyde. Now we just have to number and name the substituents. We have 2 methyl groups at carbon 2, so this would be a 2,2 dimethyl. We have 2 bromines at carbon 5, so that would be a 5,5 dibromo. And remember, when we're alphabetizing our substituents, we ignore all prefixes except for isocycloenol, none of which are present in this molecule. And so we're going to alphabetize the dimethyl according to the letter M and the dibromo according to the letter B. When we put all that together, we get 5,5 dibromo, 2,2 dimethyl hexanyl. Remember that there are no spaces between letters in names. So it's not dimethyl space hexanyl, it's dimethyl hexanyl. We separate numbers by commas, and we separate numbers and letters by hyphens that you see here in the name. Let's give the next one a try. You can see we've got 2 stereocenter, so we're going to have to get to work on this one. This is a ketone. We want to identify the longest carbon chain that contains that carbonyl of the ketone. 1, 2, 3, 4, 5, 6. So this is some kind of 2-hexanone. Again, you could either label this as a 2-hexanone, or you could call it hexan-2-one. Either one is perfectly acceptable. We have a methyl group at carbon. Let's see here. We got 1, 2, 3, 4, 5, 6. We have a methyl group at carbon 5, but that's not a chiral center, right? Because this carbon has 2 methyl groups, so that is definitely not a chiral center. So we don't have to worry about the chirality at the 5-methyl, but we also have methyls at carbons 3 and 4, and we need to designate the stereochemistry at carbons 3 and carbons 4. Let's start with carbon 3. If we draw in the hydrogen, which I find is handy to do a lot of the time, you can see that this carbon here is going to take priority number 1. The hydrogen will take priority number 4. This carbon is going to take priority number 2, and the methyl group will take priority number 3. So we go from 1 to 2 to 3 to 4 like that, which is S, but the hydrogen is coming out in front. And so at carbon 3, we have our stereochemistry. Let me delete some of this. In fact, let me delete it all so we can look really clearly upon the 4th carbon. So 1, 2, 3, 4. So now we're going to look at this carbon, the one that I have the red star by. Okay, we've got our hydrogen coming out in front. It's going to be the lowest priority. This is going to be first priority. This will be second priority, and this will be third priority. So if we go like this, it's going clockwise, which would be R. But again, our hydrogen is coming out in front, and so this is 4S. Yeah, 3R, 4S. And then we have our 3 methyl groups. We have a methyl group here, here, and here. And so it's 3R, 4S, 3, 4, 5, trimethyl 2-hexanone. Okay, if you're a little bit rusty on your Kahn-Ingold Prelog rules for assigning stereochemistry, you might need to go back and take a look at chapter 5, okay, which deals with stereochemistry. The next compound is a cyclopentanone. How did I know that? Well, I have the longest carbon chain being this 5-carbon ring. So this is some kind of cyclopentanone. We can do this one pretty fast because we have substituents where we got 1, 2, 3, 4, 5. We've got 4 methyl groups. So we have, just delete those. We got 2, 2, 5, 5, tetramethyl cyclopentanone. All right. Any questions about those? Okay, well, let's try question 19.3, which deals with ketones that have more than one carbonyl in the compound. I'll just help you out with this. If you have two carbonyls, you call it a dione. If you have three, you call it a trione. If it's four, it would be a tetraone, so on and so forth. I don't think there's any examples of a tetraone or anything beyond that. I think in our class, or in our textbooks, sorry, we mostly stick to diones and triones. Anyhow, if we were to have this compound, this would be cyclohexanone. Now, if we have two carbonyls like this, there are a number of possibilities, right? We could have them like this. We could have them opposite in the 1,4 position, or we could have them like this in the 1,3 position. And so locants are going to be important in this name. So we're going to call this 1, 2, 3, 4. And so this molecule would be 1,4 cyclohexane dione. 1,4 cyclohexane dione. Again, I tried to exemplify this with this example right here, which is a butane dione. So we don't drop the letter E. We leave the letter E on the suffix. Again, this compound has 1, 2, 3, 4 carbons, and then we just add dione on it. Same thing applies here. We looked at the longest carbon chain. This is a symmetrical compound. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is some kind of non-named trione, and we have carbonyls at carbons 2, 5, and 8. So this compound is 2, 5, 8 non-named trione. Okay, that covers nomenclature for aldehydes and ketones. The best way to master nomenclature is to simply practice as much as possible. Now we're going to switch gears and get into synthesis. And if you've been paying attention, which I know you have, throughout the year and throughout the semester, you probably noticed that we've looked at several reactions in Organic Chemistry 1 and 2 that dealt with the synthesis of both aldehydes and ketones. We're going to review those reactions quickly right now. And in the slides, I also have a reference to where you can find more information about these reactions if you need to review them. The first one is the oxidation of a primary alcohol. When we oxidize a primary alcohol, either using pyridinium chlorochromate, that's PCC, or des-Martin periodinane, which is DMP, either one is in dichloromethane, we oxidize a primary alcohol to an aldehyde. Another option is to use these conditions here, which is the Swern oxidation. The first step is dimethyl sulfoxide and then oxalochloride together, followed by treatment with triethylamine. When treated with a strong oxidizing agent, primary alcohols are normally oxidized to carboxylic acid. That's if you treated them with something like chromic acid or permanganate followed by acid. Formation of an aldehyde requires these special mild oxidizing agents that are shown here. And these are not going to further oxidize the aldehyde. So the buck stops here. We stop at the aldehyde. Another reaction that we looked at that ended up resulting in the formation of an aldehyde was the ozonolysis of an alkene. Now keep in mind that in our alkene, we have to have at least one hydrogen on that double bond in order to produce an aldehyde. How do we do the ozonolysis of an alkene? Well, this is something that you would have learned in Chemistry 3101, way back in Chapter 8, is ozonolysis, followed by treatment with dimethyl sulfide. Another way that we saw to prepare an aldehyde was by the hydroboration oxidation of a terminal alkyne. You might remember that for that, we had to use a hindered borane, like 9-BBN, or we can simply write R2BH as is shown here. And again, if you want to put 9-BBM, that's perfectly acceptable. And what this does is an anti-Markovnikov addition of water across the alkyne to produce this enol, which undergoes tautomerization, which is an isomerization by the migration of a proton in a double bond, to form the aldehyde. Back to chapter 12 again, which dealt with alcohols. It was the first big chapter that we did in Organic Chemistry 2, Chemistry 3111. The oxidation of a secondary alcohol. We form chromic acid in situ by treatment of sodium dichromate with sulfuric acid and water. And it says here that you have a whole variety of strong or mild oxidizing agents that can be used to oxidize a secondary alcohol. And the reason why is because the secondary alcohol will not undergo further oxidation. If you've read the entire chapter, you know that there's a little exception to this, but we'll look at that at the very, very end of the chapter. Next is the preparation of a ketone via that same ozonolysis reaction. And the way that this works is if we have R groups here, we have two R groups on, or at least, two R groups on one of the carbons of the carbon-carbon double bond, right? If we have two R groups, then we can end up with a ketone or a ketone and an aldehyde, depending on the situation. But anyhow, tetrasubstituted alkenes are cleaved by ozonolysis, treatment with ozone followed by dimethyl sulfide, and then we form a ketone. One more is the formation of a methyl ketone. A methyl ketone, and why do we call it a methyl ketone? Because it's a ketone, and it's got a methyl group, so a methyl ketone, and that was via the acid catalyzed hydration of a terminal alkyne, or another way you might want to phrase it is just a Markovnikov addition of water across a terminal alkyne. You end up forming this enol, which undergoes tautomerization. Again, the isomerization by the migration of a proton in a double bond to form the ketone. All right. I think there's only one more reaction that you would have learned. I might misspeak. I don't remember. Yeah, okay. This is the last one. It's the Friedel-Crafts acylation reaction. This is something that we learned in the very last chapter that we looked at on aromatic chemistry, where we can take benzene, treat it with an acid chloride and a Lewis acid, and we end up making an psyllium ion, and then the aromatic ring behaves as a nucleophile. It attacks the psyllium ion, which is an electrophile. You make the rhenium ion or the sigma complex, followed by restoration of aromaticity to form a ketone. And so there we go. These are all reactions that you learned in previous chapters. So the best way to learn these is probably dependent on the student. For some people, it might be flashcards. For some people, it might be some sort of meditation or something, or maybe making a song. I don't know. All kinds of students find all kinds of different ways to learn things, and that's definitely good. That's definitely a good thing. All right, let's take a look at these reactions. I don't want to spend a lot of time on these because these are all reactions that you should have been able to, or transformations that you should have been able to complete before beginning this chapter. The first one, we're taking a secondary alcohol and we're converting it to a ketone. Many options here. We could treat it with sodium dichromate, sulfuric acid, and water. That's one option. Other options are things like if you want to use pyridinium chlorochromate and dichloromethane, that'll work. If you wanted to do a Swern oxidation, or dimethyl sulfoxide and oxalyl chloride, followed by treatment with triethylamine, that will also oxidize that secondary alcohol to a ketone. The next one is the oxidation of a primary alcohol to an aldehyde. I'm just going to copy and paste what I wrote over here. Okay, we can't use chromic acid because if we were to try to use chromic acid here, we would end up oxidizing to a carboxylic acid. But either one of these strategies will work for oxidizing a primary alcohol to an aldehyde. Next, we have a terminal alkyne. Why is it called terminal? Because it's at the end of the molecule, right? We have a hydrogen here. We want to take that terminal alkyne and convert it into a ketone. We have to do a Markovnikov addition of water. So this is Markovnikov addition of water. And the way that we do that is by treatment with sulfuric acid, water, and mercuric sulfate, HgSO4. And lastly, we have the formation of an aldehyde from a terminal alkyne. This is the result of anti-Markovnikov addition across that triple bond. How do we do that? We treat the molecule first with 9-BBN, which seems to be the favorite of my students. If you like to write a hindered borane, just some generic hindered borane, there are several of them out there that we don't look at in this class. And then follow that by treatment with hydrogen peroxide and sodium hydroxide. There we go. Okay, again, this is just a review of reactions that you've already learned in this class, where we end up forming aldehydes and ketones. So nothing new there. Okay, let's switch gears again and get into section 19.4, which deals with nucleophilic addition reactions. Now, why are nucleophilic addition reactions so important in this chapter? Well, it's because a carbonyl is an electrophile, right? And we've seen a carbonyl behave as an electrophile many times in this class before. If you take a look at the resonance structure, and if you look at the inductive effect of that carbonyl, that gives us a rationale as to why a carbonyl is such a good electrophile. Take a look at the resonance structure. First of all, this resonance contributor here has a positive charge right on the carbon, so that's definitely electrophile, right? Seeking electrons. And if you look at the inductive effect, whether you choose to draw a dipole arrow, or if you choose to draw, delta pluses and delta minuses, which represent the unequal sharing of electrons between the carbon and the oxygen, because the oxygen has an electronegativity of 3.5, and the carbon has an electronegativity of 2.5. Well, you can clearly see that oxygen is going to have more of that electron density pulled towards itself, which renders that carbon electrophilic. So no matter which way you slice it, whether it's with resonance or induction, you can clearly see that carbonyls, whether they're on aldehydes or ketones, are electrophilic. So of course they're going to react with a nucleophile. Now, what about the molecular geometry of an aldehyde or a ketone? Now, what's drawn here in this blue sort of square is a ketone, but the same rationale applies for an aldehyde. The carbon in an aldehyde or a ketone, okay, the carbonyl carbon is sp2 hybridized. If it's sp2 hybridized, what is the molecular geometry of that carbon? It's trigonal planar. And that's why they put this kind of blue square here, okay, to kind of show you that it's flat. And if it's planar, that means a nucleophile can attack from either the top face, as is shown here, or the nucleophile could even attack from the bottom face, like that. What's the net result of nucleophilic attack possibly occurring from the top or the bottom? Is that if you had, two different R groups, you could end up with a racemic mixture. Now, if we compare the reactivity of aldehydes to that of ketones, we see that aldehydes are actually, generally speaking, more reactive towards nucleophiles. And there's two reasons why. The first one is usually abundantly clear to students. If I ask my students, why do you think an aldehyde would be more electrophilic? They'll say, well, it's definitely less sterically hindered because it only has a little proton on one side, and a hydrogen atom is the smallest atom in the whole periodic table. So it makes sense that, yeah, an aldehyde is less sterically hindered, therefore it's more susceptible to nucleophilic attack. Okay, well, that's one reason. Another rationale is based on electronic effects. Remember that R groups, alkyl, are electron donating through hyperconjugation. If I have two R groups in my ketone, both of those R groups are donating some electron density towards that partially positive carbon. What does that do? It renders that partial positive charge a lesser partial positive charge, which renders it less electrophilic. Whereas the hydrogen atom doesn't have that capability of stabilizing that partial positive charge. The aldehyde only has one electron donating alkyl group, again, electron donating via hyperconjugation, and therefore it renders the positive charge on the carbonyl of the aldehyde significantly more positive and thus more susceptible to nucleophilic attack. Some nucleophiles require acidic conditions, others require basic conditions. Here's an example of a reaction that requires basic conditions. A Grignard reaction, right? This goes all the way back to Grignard chemistry. If we take a ketone and treat it with this Grignard reagent, methyl magnesium bromide in water, what's going to happen is our methyl magnesium bromide, and again, we could write CH3, we can write that like it's a carbanion, and we're going to get this carbanion is a nucleophile to attack the oxygen, and then the second step is protonation. I'm not drawing that in, but this requires basic conditions. Why would that be? Why would this require basic conditions? Because remember, if the methyl anion, okay, if the CH3 with the minus charge, if that sees any kind of acid, even a weak acid like water or an alcohol, it's going to simply deprotonate. That's why we covered protecting groups in the alcohols chapter. Generally, a strong nucleophile means the reaction is under basic conditions. This should be capitalized, shouldn't it be? Grignard should have a capital G. Under basic conditions, all nucleophiles react with carbonyls by the same general mechanism. And this is what we just saw. I drew the first step in the Grignard, and of course the last step is going to be a proton transfer. And that's why the first step in that Grignard that we looked at on the last slide, right, was to treat the compound with methyl magnesium bromide. That's step 1 over here. And then step 2 was to treat it with water, okay, for the proton transfer. The nucleophile attacks, we form the negatively charged intermediate, shown right here, and then is protonated upon acidic workup. Aldehydes and ketones react with a variety of weaker nucleophiles under acidic conditions, but by the same general mechanism. However, the first step is not the nucleophilic attack. The first step here is going to be a proton transfer. Now, why would that be? Because when you protonate the carbonyl, you generate an oxonium. That's shown right here. I have a question for you. If I compare this ketone versus this protonated ketone, which one of these would be more electrophilic? Not a trick question. Absolutely, David. Yes, it's going to be the oxonium, right? Thanks, Skylar. Good. Yeah, and it's because you can see that overall it's got a partial, or it's got a positive charge. Of course, it's going to be more electrophilic if it's positive, right? So it even says it here in the text. When it gets protonated, it renders it even more electrophilic and susceptible to nucleophilic attack. And after the nucleophiles attacks, then we form an alcohol. Acidic conditions are required in order for a weak nucleophile to attack a carbonyl carbon. We're going to see this many times throughout this chapter, that in order for a weak nucleophile, like an alcohol or a thiol or an amine, to react with a carbonyl, we have to protonate it first, and that renders it more electrophilic. In fact, it turns it into a very powerful electrophile. You want to keep that in your mind as we progress throughout the chapter. When a nucleophile attacks a carbonyl group, though, the equilibrium of what's going to happen depends on the ability of the nucleophile to function as a leaving group. Now, if we were to use HCl, HCl is an acid, absolutely. HCl can protonate a carbonyl, no doubt about that either. But if the chloride comes in and attacks as a nucleophile, that can happen, but what else do we know about chlorides? Chloride is also a good leaving group. Not just a good nucleophile, it's a good leaving group. And so the equilibrium in this case is actually going to favor the starting material. It's actually going to favor the starting ketone. So this isn't going to be a very useful reaction. We're going to cover the following nucleophiles and the reactions with ketones and aldehydes. We'll talk about oxygen nucleophiles like water, alcohols, and diols. We'll talk about hydrogen sulfide and thiols, or dithiols, I should say. We'll talk about amines, whether they be primary or secondary amines. Notice that this is a primary amine, this is a secondary amine. We'll talk about hydrogen nucleophiles like lithium aluminum hydride and sodium borohydride. And then finally, we'll talk about carbon nucleophiles, which will result in the formation of new carbon-carbon bonds. The green yard is old hat, something you've seen before. We'll also look at cyanide as a nucleophile, and this interesting species down here, which is called an ylide, which results in the formation of new carbon-carbon double bonds. And we'll study that reaction in detail. It's called the Wittig reaction. Okay, let's get started on section 19.5, which deals with oxygen nucleophiles. I'll give you a few seconds to have a break here, because this is a pretty long and involved section. Another thing I can, kind of put in your ear is that I've looked at enough standardized tests on organic chemistry to know that the ACS, MCAT, DAT, PCAT, those kind of exams, they love to test students on oxygen nucleophiles. So this is going to be exceedingly important. Okay, very important section. All right. If you take a ketone or aldehyde and you put it in water, take an aldehyde like formaldehyde, or a ketone like acetone or 2-hexanone, whatever. Okay? If we put that in water, it's going to be in equilibrium with what's called a hydrate. Hydrate's a new functional group. When we have two hydroxyls, or it looks like two alcohols on the same carbon, that's called a hydrate. You have to be fully aware of what a hydrate is. The equilibrium, though, and that means this equilibrium here, generally speaking, does not favor the formation of the hydrate. The only time the hydrate is really favored is when you have really simple aldehydes like formaldehyde, okay? The rate of reaction is going to be slow unless acidic or basic conditions are used. Under basic conditions, a hydroxyl is going to be, or the hydroxide, is going to be the nucleophile. Again, hydroxide, as we've seen many times throughout this class, is a strong nucleophile. Of course, it's going to attack the carbonyl of this aldehyde, formaldehyde. We end up with the negatively charged species right here, and then that undergoes a proton transfer to form our hydrate. To remind you, this is a hydrate. And this is a base catalyzed hydration of an aldehyde. What about acidic conditions? Same starting material, same product, but now we're in an acidic environment. So what's going to be the first step? When you're in acid, the first step is going to be that proton transfer onto the oxygen of the carbonyl to render it more electrophilic, producing the oxonium. After you've produced the oxonium, water, which is not a powerful nucleophile, can react with this strong electrophile to produce this second oxonium intermediate, which gets deprotonated by water. So to summarize, we've looked at the formation of a hydrate from an aldehyde. In this case, it was formaldehyde in both of these examples, but from an aldehyde or a ketone in basic conditions and acidic conditions. And we've looked at both of these mechanisms. Now, I'm not going to write on every page every time you need to know a mechanism, but I can promise you that these mechanisms are important. How about we do it this way? If a mechanism isn't important in this chapter, I'll let you know. This is a slide that always comes up. This is written by Dr. Klein himself. Now, Dr. Klein is an excellent organic chemist, okay, one of the best there is. And he always puts this in his book. I don't see students making this problem a lot, not a lot, maybe once in a while. But I want you to keep these things in mind when you're drawing mechanisms. If you're in acidic conditions, okay, you're never going to form a strong base in acidic conditions. A strong base is not going to be able to survive in an acidic environment. The opposite is also true. If you're doing a reaction mechanism and you're drawing it in basic conditions, you're not going to produce any strong acids. Again, it's not something I see my students doing a lot of, but it might be something you want to be cognizant of when you're trying to draw the mechanisms that we look at in this class, which involve a lot of proton transfers and nucleophilic attacks. Okay, let's get back to it. Here's a new functional group that you have to be aware of. In fact, this is a functional group that's going to come up a lot In fact, we're going to look at the entire mechanism of this reaction here, where an alcohol can attack a ketone or an aldehyde to form what's called an acetal. And the way that works is we take our ketone or aldehyde here, they're showing a simple ketone, acetone. We have to react with 2 molecules of the alcohol. So you can see the stoichiometry is 1 to 2, and then we produce 1 molecule of the acetal and 1 molecule of water. When I teach this reaction in nursing chemistry, where we don't cover mechanisms, I tell my students, an acetal is kind of like you have 2 ethers on the same carbon, and that might be something you want to think of, okay? Another way you could think of it is that it's like a hydrate, but you have an R group in place of a hydrogen, okay? An acetal. Under acidic conditions, 1 ketone or aldehyde reacts with 2 alcohols to form an acetal. Now, the acid that's used in this reaction, you can see that it's inside these square brackets. The square brackets mean that it's a catalytic amount. So we have the acid operating as a catalyst. So we don't have to add, 1 full equivalent. For example, and this is just an example off the top of my head, if you had 1 equivalent of the ketone, 2 equivalents of the alcohol, if it says a catalytic amount of acid, you could get away with, 0.1 moles, okay? So you don't have to add a lot of the catalyst because it gets recycled over and over. Commonly used acid catalysts for acetal formation are para-toluene sulfonic acid, which the book abbreviates as TSOH. It's also called tosic acid. It's also called PTSA. The reason PTSA is such a great catalyst is because it's a solid at room temperature. Right? It's a lot easier to walk over to. All my students who are in 3112 know it's a lot easier to go to the balance and weigh a solid out than it is to grab a volumetric pipette and try to finagle something like sulfuric acid. Now, mind you, you don't have to be very careful when it's acting as a catalyst. You can just throw in some and kind of walk away. But toluene sulfonic acid is a lot easier to handle than sulfuric acid, and that's why it's commonly used. Also, this isn't covered in the book, but PTSA, when you use it, it always has to be freshly recrystallized. And if you're rolling your eyes thinking, oh no, not a recrystallization, those are the worst. Well, PTSA is recrystallized from water, and it's really easy to recrystallize. Okay? It's probably one of the fastest recrystallizations that you could possibly do. Here's the mechanism of the formation of an acetal from a ketone or aldehyde. Now, again, they're showing a ketone here. But besides the acetal, there's one more new functional group I need you to know, and that's a hemiacetal. Very important because hemiacetals come up a lot in carbohydrate chemistry, which we're going to look at in chapter 24. The first step is a proton transfer to protonate the carbonyl to render it more electrophilic. Then we get a nucleophilic attack of the alcohol. We form an oxonium, which gets deprotonated. And then we end up forming our hemiacetal. Now, Dr. Klein likes to break up this mechanism kind of into 2 steps. He says you can think of the first, or 2 sequences, I guess. You can think of the first part as the formation of a hemiacetal, and then you kind of repeat that sequence, in a way, in that first you protonate the alcohol, or the hydroxyl, to form a good leaving group, and then you eject the leaving group in this step. So here's your loss of leaving group. Then you have a really electrophilic carbon on that to that doubly bound oxygen, the oxonium, and then you do another proton transfer, and there you have it, the acetal. Look, I know this looks like a big mechanism, and it is, but you need to be fully aware of this mechanism. And you might be wondering, well, if the exams are multiple choice, or if the quiz is multiple choice, or if the ACS final is multiple choice, how do they ask questions about this? Well, most of the people who are hearing the sound of my voice took the ACS final for Organic Chemistry 1, and you know that they have ways of asking about mechanisms. They'll ask you, which step is reasonable, which one of these is actually a step in this mechanism. And so I would highly recommend practicing this mechanism. Practice will make perfect. acetal formation is an equilibrating process. Now, you might be wondering about this. For most simple aldehydes, the acetal is favored. Okay, and you can even see that exemplified by these equilibrium arrows here, that the equilibrium is lying to the side of the product. But what about a ketone? With a ketone, the acetal is not favored at equilibrium. Now, how could we push that reaction forward? I can tell you that in the book, he says that the water is removed using a special technique, I think, or something like that. But if you remove the water, think about Le Chatelier's principle. If you lower the concentration of this by removing it, it's going to push the equilibrium to this side. And that is how we produce acetals. I've done it many, many times in my life. And if you're curious as to how you remove the water, you could Google this and just look it up if you wanted. You use what's called a Dean-Stark apparatus. Okay? And it's just an apparatus that's used to remove water. And there are other options besides the Dean-Stark apparatus, which is nothing more than a special piece of glassware. You could also use what are called molecular sieves, which are a zeolite. They're like an innocuous solid that absorbs. So a water absorbent. There you go. That's enough. Okay, there's something that just absorbs water, so it's not going to interfere with the reaction, and that's going to drive the reaction forward. So we do have ways of pushing these kind of reactions forward. And if you're wondering why I'm yammering on about this, it's because I don't want you to think, okay, well, the equilibrium lies to the side of the reactants. How does this even work? Right? Organic chemists are very sneaky, and they've developed lots of ways to push reactions forward. Now, what about if you use a diol? Right? Let's go back here. Okay, let's go back here. To form the acetal, okay, here's our acetal. We used 2 molecules of the alcohol. So 2 molecules of ethanol in this case, and we made, these ethyl, with these ethyl groups on the oxygens here. Well, what if I had the 2 alcohols in the same molecule? Well, you guys know this molecule. We talked about it in chapter 12. This molecule here is antifreeze. This is ethylene glycol. It's a diol. If I did the same reaction mechanism, which is 3 steps followed by the 4 steps, okay? And if you don't believe me, I don't know if I pointed that out. If we back all the way up here, you can see that we have 1, 2, 3 steps to form the hemiacetal, followed by 1, 2, 3, 4 steps to form the acetal. So that's what it means by the 3 steps and the 4 steps. You can make what's called a cyclic acetal. Now, cyclic acetals are actually exceedingly useful in organic chemistry. Very, very useful. Let me show you why. The acetal formation is a reversible reaction. We've looked at a couple of reactions that are reversible. Think about the formation of a sulfonic acid that we looked at in chapter 18. We formed the sulfonic acid by treatment of an aromatic ring with sulfuric acid. Then we removed that sulfonic acid, the SO3H, using dilute sulfuric acid. If we take a ketone and we treat it with ethylene glycol in an acid catalyst, and the minus H2O, this just means remove the water. Okay, we form an acetal. But we can blow that acetal off pretty easily. All you have to do is treat the molecule with water. Okay, you throw in some water, and what did we say? We said the equilibrium is going to lie to the side of the ketone, generally speaking, anyway. So it's kind of a neat reaction, or a neat sequence of reactions, I guess. To favor the acetal formation, again, we remove the water, okay. And then to convert the acetal back to the ketone or aldehyde, you just add water with a little bit of acid catalyst. In this way, acetals can be used as protecting groups for ketones and aldehydes. Where did that word protecting group come up in this class before? It came up in chapter 12, when we protected an alcohol with a silyl ether, like trimethyl silyl ether, in Grignard chemistry. So now we're going to see, why would you want to protect a ketone or an aldehyde? Is there a good time to do that? The answer is yes, absolutely. What if I asked you to do this reaction right here? I said, you've got this bifunctional compound. You have 2 functional groups. You've got a ketone here, and you have an ester here. You want to reduce the ester to a primary alcohol but you want to leave that ketone intact. Now, we learned how to convert an ester into an alcohol, right? If we were to take an ester, okay, like this, and we treated it with LAH, okay, followed by workup, okay, we end up forming an alcohol. You might think, okay, well, that's good, but what's the problem with that? You would also reduce the ketone to a secondary alcohol. Okay, is there a solution? Absolutely, there is. We're going to use a protecting group for that ketone. What's the protecting group? It's going to be an acetal. First, we protect the ester, first we protect the ketone rather, as the cyclic acetal by treatment with ethylene glycol, an acid catalyst, and water. Removal. There's our cyclic acetal. And then, after we do the reduction using lithium aluminum hydride, the second step of the reduction with lithium aluminum hydride, which is the same thing as LAH, okay, we treat that with water or acid. I think in the book sometimes it says H2O, but H3O plus works as well. Not only will it serve to work up the lithium aluminum hydride, it's also going to remove the cyclic acetal. So it's kind of a 2-for-1, right? Two steps at once. The one step, two step, right? Anyhow, give me a thumbs up if you follow me on this on the sequence. I know I haven't. There's a lot of content to cover in this chapter. We are going to look at a question in a few seconds. We'll look at a few questions. Okay, good. Again, I'm fully aware that it's a lot of talking today. Fully aware of that. Okay, thumbs up. Thanks, David. Good. All right. Hemiacetal. Let's talk a little bit more about hemiacetal. So I just kind of threw that functional group at you and said you have to know what it is. A hemiacetal is the intermediate form in the conversion of that ketone or aldehyde to an acetal, kind of like the halfway point. Hemiacetals are actually quite difficult to isolate, depending on the molecule, because the equilibrium is generally speaking going to either favor the aldehyde or ketone or the acetal, depending on what kind of conditions that you use. However, and this is really important with respect to carbohydrate chemistry, which is chapter 24. And so, of course, we're going to look at this in even more detail later on. Cyclic hemiacetals can usually be isolated. What do you mean by a cyclic hemiacetal, Mr. Dion? Let me show you. If you have that oxygen nucleophile from the hydroxyl and a carbonyl in the same molecule, well, you can see how after protonation, if you form your oxonium, this can act as a nucleophile like that, right? Anyhow, after several more steps, I'm obviously leaving out a bunch of steps from the mechanism, you form this cyclic hemiacetal. Now, why would this cyclic hemiacetal be so darn great? It's because you have a 6-membered ring, right? A 6-membered ring, and the hybridization of all the atoms in that ring is sp3. So all the carbons are going to have a tetrahedral geometry. The oxygen will have a tetrahedral electron geometry. It will have a bent geometry, but all of the bond angles are going to be close to 109.5 degrees. And that's why the formation of that cyclic hemiacetal is favorable. That's important because glucose, which is shown here in the open chain form, actually forms a cyclic hemiacetal. And in fact, if you've studied biology, you're probably used to seeing glucose drawn in this chair form right here. Again, we'll talk about that more in chapter 24, but it's still important that you know that. Now let's get into trying a practice problem. And that is apply the following transformation. Converting cyclopentanone into this acetal. It says we're using sulfuric acid as our acid catalyst and excess methanol, and of course we're removing water. Well, the first thing we're going to do is we're going to protonate that carbonyl to render it more electrophilic. What's my acid catalyst? Now, I'll be completely honest with you. It depends on where you look. If you're the kind of person who likes to surf the internet and look up mechanisms there, totally fine. You might see somebody just draw H plus like this, okay, just out of the blue. And if you're a professional organic chemist, I would say that's okay to draw that in, maybe a meeting or something. If I was talking to Dr. Schaafstal and I drew that, he'd be like, yeah, no problem. But when we're learning organic chemistry, what I want you to understand is that when you take sulfuric acid, right, which is a very strong acid, and you mix it with methanol, right, what's it going to do? It's going to protonate that methanol. You're going to end up with this, right, plus the conjugate base of sulfuric acid, like that. Sulfuric acid has a pK of around -9, and the pK of the protonated methanol is around the pK of hydronium, which is around -1.7. We'll just call it -2. And so you can see how the equilibrium is going to lie to the side of the weaker acid. Therefore, to correctly draw the mechanism, you would draw a protonated methanol like this, or the oxonium of methanol, and you would draw your curved arrow like this. Okay, so remember that all of these steps are in equilibrium. We push the reaction forward by removal of water. Let's draw the protonated carbonyl, or the oxonium, like that. Now I've rendered this carbon very electrophilic. Do I have a good electrophile or a good nucleophile? Well, when I deprotonated this protonated methanol, I produced methanol. So now my methanol, CH3OH, can act as a nucleophile, and it's going to attack like that. Let's draw what we would end up with as our product. Hopefully I don't run out of space here. And I find it hard to write on the bottom of this thing, but anyhow. There we go. Like that. Now we're going to have to do another proton transfer, and so another molecule of methanol is going to remove that proton from the oxonium. This. Now we're going to end up with what? Our hemiacetal. Let's draw it. The hemiacetal is going to look like this. We're going to have our hydroxyl here. We're going to have our OCH3. Now, remember, we're going to have to lose water. Where is that water going to come from? In fact, the water is going to come from here after it gets protonated. Right? When I did the last proton transfer, I ended up forming more of the protonated methanol. And so that can act as an acid catalyst to protonate the hydroxyl and render it a good leaving group. Let's draw that. First, we'll start by drawing our protonated methanol like this. Put in the lone pairs on my oxygen. Do this proton transfer like that. Now I've converted that hydroxyl into a good leaving group. Let's draw that. It'll look like this. I'll just condense it like this. Okay. And then I have my OCH3 like that. Now I'm going to lose that water. And the way that you lose the water is that this lone pair from the oxygen is going to serve to eject the water molecule like that. Then we end up with this, where we have a double bond to our oxygen, and we have our methyl here. Now we've rendered that carbon strongly electrophilic again. Now methanol can come in as a nucleophile. So another molecule of methanol, it's going to come in as a nucleophile like this. We end up with one last intermediate. Kind of playing dangerously here with my space. We end up with this intermediate like this, OCH3. And then the last step is the proton transfer. I'm going to have to delete my pKa values here. There we go, like this. And then the last step, the last molecule of methanol comes in, and it's going to remove this proton at the end. And what's that going to form? When this methanol takes on this proton, you're going to regenerate this catalyst over again. You can see how you could break this mechanism up, and this is the way Dr. Klein likes to do it, into 1, 2, 3 steps. The formation of the hemiacetal, and then 1, 2, 3, 4 steps, like that. Okay, this is the kind of mechanism where I could sit here and yammer on about it like I just did, but I could yammer on about it for days and days and days. You're going to have to practice drawing it on paper in order to master that. Let's talk about some syntheses here in question 19.10. Propose an efficient synthesis for each of the following transformations. The first one involves the formation of a new carbon-carbon bond right here, like this. Now, how did we do that, generally speaking? If we wanted to deprotonate here in the alkynes chapter, we always treated it with sodium amide, right? NaNH2. But what's the problem with that? NaNH2, the amide is going to be a good nucleophile, and it could attack the carbonyl like that. And so that's not going to help us because we want to keep that carbonyl intact. Thus, we're going to have to protect the carbonyl. How would we do that? We would do that by the formation of a cyclic hemiacetal. The first step would be to treat the compound with ethylene glycol, an acid catalyst. We make sure to include the removal of water. It's a convention. That would produce our cyclic hemiacetal. Sorry, our cyclic acetal. Next, we're going to treat it with sodium amide to do the deprotonation, followed by ethyl iodide because we're adding an ethyl group to the molecule. And then finally, we're going to remove that cyclic acetal using acidic conditions. So just by treating it with acid, like that. Let's give the next one a shot. What we're doing here is we're adding two phenyl groups to this carbon on that ester. You might remember that the way to do that is to treat the ester with excess Grignard, followed by treatment with acid or water. Now, the problem with that is if we were to treat this molecule with excess Grignard, Grignards react with ketones and esters and aldehydes. So we're going to have to protect that ketone first. How would we do that? First, we would treat it with ethylene glycol, the same protecting group, in fact, the only one that we learned for a ketone, followed by removal of water. That would produce this intermediate, the cyclic acetal. We still have our ester intact. Then we would treat it with excess phenyl magnesium bromide. I chose that because I'm adding phenols. Followed by treatment with acid, H3O plus. Now, I just want to point something out. If you're a real stickler about what we learned in chapter 12, whenever we did a Grignard in chapter 12, I didn't use hydronium. I always said water. Well, in the next edition of Klein's textbook, which is coming out next fall, you'll miss it, instead of putting water as the second step in a Grignard reaction, he puts H3O. Correct, okay, because you do need an acid. Now, if you treat this molecule with H3O plus for your workup, what's that going to do is not only it's going to work up the Grignard chemistry, but it's also going to remove the cyclic acetal, and you'll end up producing the desired compound. We still have 40 minutes left. Let's talk about nitrogen nucleophiles. This is section 19.6. I realized that section 19.5 is a heavy section. There's a lot of new chemistry in that section. The big mechanism in that section is the formation of the acetal, which is a mechanism you have to be fully aware of, and you have to be able to draw that mechanism. But the good news is that same mechanism comes up again in this chapter. David asked me a question: how do you know that you've removed the water? There are several ways you can monitor it. One way would be to monitor the reaction by TLC. That's something you're probably used to doing in the lab. That's probably a very simple way. Another way that chemists monitor reactions is using liquid chromatography mass spectrometry. Now it's not beyond the scope of our course by any stretch of the means, but there's an even simpler way, David, and I'll show you what it is. Just give me 1 second. Can you see my screen? Okay, just give me 1 second then. Sorry, I'm not good at using my iPad for anything but teaching. Let me go back here. Oh, that's not where I wanted to go. Here. It's a really good question, David. So I think it's worth looking at as a group. Can you see my Google page, what I just Googled with my iPad? Yeah, so I Googled the Dean-Stark apparatus. Now, I don't know if I can write on this. In fact, no, I can't. But let me just zoom in on one picture. Maybe this one. Yeah, so this is a Dean-Stark apparatus. And without me going through all the nuts and bolts, think back to general chemistry. If I was to give you a certain number of moles of your ketone or aldehyde and a certain number of moles of your alcohol, and of course your acid catalyst, but that's not going to be the limiting reactant or anything, based off of the molar quantities of your ketone and aldehyde, you would be able to calculate the number of moles produced of your water. If you have the number of moles of water that you should get when the reaction is complete, you can convert that number of moles into the number of grams of water. Using the density of water, which is pretty close to 1, you could calculate the volume of water that you should get produced from the reaction when it's complete. And so, in fact, the easiest way to monitor these reactions is to use the Dean-Stark, because the water ends up going into this part that you see on the left-hand side of this piece of glassware, and you can actually watch the volume. So let's say you were doing the reaction and you said, well, when the reaction is complete, I will have produced 12 milliliters of water. You're going to do the reaction in a solvent that is not miscible with water. We normally do it in a solvent like toluene. And so you'd be able to see the water gathering at the bottom. In fact, that's why there's a stopcock at the bottom, is if you were to make more than 20 milliliters or a lot more, you could drain it off gradually and measure it. So does that answer your question? You could actually literally measure it with this graduation on the glass apparatus, and you could calculate exactly how much water you should produce. It's a really cool piece of glassware. Yeah, okay, good. Glad I answered your question. Okay, we only have 5 minutes left, but we could talk about nitrogen nucleophiles quickly. And the reason why I want to go over this, and of course, I'm not going to go over it quickly, but it's because there's a few new functional groups that you have to be aware of in the nitrogen nucleophile section. And the first one is called an imine. If you take an aldehyde or a ketone and you treat it with a primary amine, now this is very, very important, okay, because we're going to look at a different functional group that's formed when you treat an aldehyde or a ketone with a secondary amine using the same types of conditions. So primary amine, you end up with forming what's called an imine. Another name for an imine, and if you were to go up to an organic chemist and say an imine, they're going to know what you're talking about. But I worked with a lot of guys who were born in the 40s, when I first started my career, and they would never call it an imine. They always called it a Schiff base, okay? And it's named after a scientist or a chemist named Hugo Schiff, who discovered the Schiff base. And it's still commonly used to this day. So don't think, oh, Mr. Dion's showing me something that's old and dilapidated. Trust me, if there's one thing you should have learned in organic chemistry, is that old habits die hard with organic chemists. They love the old-timey names of everything. So a Schiff base or an imine. And we have a carbon-nitrogen double bond where that carbonyl was. Now, you might be wondering about the mechanism of this imine formation, and it's a pretty interesting mechanism. In fact, what's really interesting is the pH at which the reaction is run. But I'll just put this bug in your ear that I would like you to take a look at this mechanism before class on Monday, because it's a very important mechanism. I would like you to try to draw this, be able to draw this mechanism, and be able to recognize what's going on here. Okay?